integration by parts or use substitution, and some area problems. So building off of what we did last week we did fairly straightforward integration, things that were sort of walking back differentiation techniques that we have already learned. So that's the reverse power rule, taking the reverse of those trig derivatives that we've already learned. So the same can sort of be said about what we're going to be doing today, but so I'll detail a method of breaking it down that I'm not sure if Dr. Zlecki has presented it to you, but I've seen it presented in my own classes and when I've observed other classes being taught. And it's a way of just kind of rooting through the chaos. If you can't look at this and off the bat identify what part of this derivative is left over from the original function and what part of the derivative is, so when I say the derivative, I mean this entire phrase here, what part of this is from having differentiated. And that's why I've got this first one color coded here for us. Get my toolbar out of the way. Okay, so to start, first thing to do when we're doing use substitution is identify what our u is going to be. So that's what I was talking about when I was saying that we have to figure out what part of the function is left over from the original function, so big F in this case, and then what part of the function is part of the derivative. So, or has come about because we've taken the derivative. So more often than not, or pretty much always, it's going to be the most complicated aspect of the function that's going to be your u, going to be the original function, because if you think about the power rule, we get smaller and smaller, simpler and simpler, and that's typically the case when we take derivatives. And so in this case, what is in green is going to be our u, and if you think about taking this derivative here, we know that when we do the power rule on negative x squared, we should have a negative 2x as our derivative. And with some factors, with some constants that we can add in, this x here is going to be the leftover of the derivative, we'll say. So first we define our u. Now, as far as use substitution goes, the next thing you do is you find du. So du is negative 2x dx, and we take it with respect, so in this case, we're taking it with respect to x. If you guys remember with differentials, or sort of with Riemann sums as well, say we've got a graph that looks like this, and I took what is supposed to be an infinitesimally small, that should not have become a triangle, what is supposed to be an infinitesimally small rectangle, but that little width there, that delta x, is the same as dx. And just sort of as a visual for what that dx is, but we don't, so the reason why we have to have dx for use substitution is because, like the name suggests, we're going to substitute all of this information into the equation that we already have, and there's a dx, and there always has to be a dx when we integrate, and so we're going to get that into a workable form so that we can substitute in x dx in the purple, which when manipulated, so if we start with du, is actually equal to negative 1/2 du. So we're going to substitute, I'll check that afterwards. We're going to substitute in our u, and then we're going to substitute in our x dx, so the derivative aspect. So that's going to look like this. And now, so I want to remind you guys, part of the operations of integrals states that we can take this negative 1/2, this constant, and pop it out front, and just multiply what the antiderivative is by that negative 1/2. But I don't do that. Well, I guess I do it for this step. So I've also manipulated it and put it into u to the 1/2 rather than as a square root so that I can do the reverse power rule. And maintaining that negative 1/2, now that I am integrating, I'm doing the opposite of taking the derivative. I know that by the reverse power rule, I need to add 2 halves in order to walk it backwards. And so when I take the derivative of u to the 3 halves, which I know that's what the original function has to be, I need to add in this 2/3 here in order to account for, or to cancel out with the 3 halves for when I drop it. And that negative 1/2 is entirely different. So so these two constants are going to work together to give us our original function. And then we've got our plus c here. So the plus c, I'll remind you guys, I had a question about it in first recitation also. The plus c we use when we don't have boundaries. So if you remember from last week's recitation, I drew up a graph with a bunch of linear functions, all of these functions would have the same slope, but different intercepts. And that plus c is going to be the unique intercept. So they're all within the same family of functions, but without the specificities of the bounds to guide us to what the exact area underneath one of these graphs is, we can only say generally what the derivative would look like, or what the antiderivative would look like. So another thing I'll remind you guys of is when we are integrating, when we have this integral symbol, what's being asked of us is what's the area underneath this derivative. So say I had the area, so this here is, we'll say it's x plus 2, whatever. If I were asked to integrate this without bounds, I would have to do a plus c. If I were asked to integrate this and I knew it was from -2 to 0, then I would be finding this area here. So when we have bounds, we can be a lot more specific. When we don't, we represent the fact that we don't know exactly what this function looks like because there's a constant that will make it will give it a more specific intercept or give it an intercept at all. And that's represented with the plus c. And so then finally, circling back to number 7, we'll plug in that u at the end, and that is u substitution. So a quick walkthrough of the steps again. First thing, when you look at these problems, so we won't necessarily say on an exam, use u substitution or integration by parts to complete this problem. It could be a mixed bag of integration problems presented to you, and you're going to have to identify what method to use. So the fact that there are 2 parts to this function should tell you this is going to be an integration by parts, because we don't have a reverse product or a reverse quotient rule. And so whenever you see anything that's multiplied or divided that is next to this integral symbol, you're probably going to be using integration by parts. So then the next step would be to identify, so if we're talking trig, it's not always going to be the most quote unquote complicated aspect of the function, but if we're dealing with a polynomial here, this more complicated polynomial is going to be our original function. And so then we'll look and see, is there another part of the function that looks like it could be its derivative if I add in some or multiply by some constants, get things to shake out the way that I want to. If we're dealing with trig, it's a little bit different, but we'll do some problems here in a second and you'll see what I mean. But are there any questions so far on u substitution, or on integration by parts, I should say? All right. I do want to note, someone in first recitation asked, will I lose points if I don't use this? No, you aren't required to use this. It's just a way of breaking it down. And like I said earlier, navigating the chaos. If you can look at this and think it out on your own, that's fine. But you are still going to be expected to show your work. You can't just write the final answer per se. All right, moving on to number 9. So similar to the last one, we've got this, I don't want to say, actually it's not all that similar to the last one, but we do have, so in general, I've been saying the more complicated aspect of a function, say for dealing with polynomials, is going to be the remnants of the original function. In this case, we don't really have anything that we can identify as being less complicated, because what probably happened is, or what will happen is that our constants are going to make it shake out that this -2 derivative that we should have is not there. But still, you can sort of think of it as when we were doing the chain rule, because this is basically the reverse of the chain rule. Whatever's whatever is most central to the function, so in this case, what's in the parentheses, in this case, what's under the radicand, that's also another way of maybe directing yourself towards what aspect of the original function, what that aspect is. Because I feel like that's probably going to be, if you got this down, if you can use this u substitution, this plugging in method, and you know how to integrate, you'll probably do well at these, so long as you can identify what the correct u is. And that's often what students struggle with the most. So that's just another way of thinking, or of guiding yourself towards that correct answer. So like I said, u is going to be equal to 1 minus 2x. And so we'll take our du, which is going to be -2 dx, and then we'll get that into a workable form so that we can plug in for dx. So dx is equal to -1/2 du. And once we plug all that in, it looks like this. If you want, you can pop the constant out front. It doesn't make much of a difference, But when we integrate, we do have to maintain this -1/2. So if that's a little confusing to you, then maybe I would recommend popping the -1/2 out front so that you can focus on the integration of u to the 9th, because this 1/10 comes from the reverse power rule. If we know that if u to the 9th is the derivative, we know that the original function must have been u to the 10th. But we have to account for that, for the dropping of the 10 with this inverse fraction with 1/10. But that doesn't mean that the -1/2 isn't still equally a part of this antiderivative. So if that's confusing, maybe you should pop the -1/2 out front and just focus on the integration of the u. So we've also got our plus c. Last step is to simplify and to plug in what our u was originally. And as always with integration, it's never a bad idea to just take the derivative of what you found and make sure it matches up with what was given originally to fact check yourself. All right, moving into some trig problems. So u is typically not going to be equal to a full, so I don't want to say never, just because there may be an example out there that I haven't seen, but typically when I have taught integration by parts, I have never done a problem where u is equal to a trig function. It's usually what's inside of the parentheses. So what I said earlier holds true. Typically what's centermost to the function, what's inside the parentheses, like when we were thinking about the chain rule and working our way out, or working our way in, excuse me, is going to be what's equal to u. And in this case, that is true. We have u is equal to 2 theta over 3. And then when we take the derivative, or we take our du, we get 2/3 d theta, which when we're finding d theta so that we can plug it in is, well, d theta is equal to 3/2 du. And so now we can plug all that in. And at this point, so like I said, you can pop the constant out front. At this point, you just focus on sine. You think, okay, I know that the derivative of cosine is negative sine. So what would give me a derivative of sine? Negative cosine. We got to add in that negative there in order to balance it out. And so we keep our 3/2, we multiply by negative cosine u, and then we have our plus c here. And the final step, once again, is to simplify and plug in that original u. So I've said it twice before, I'll say it again. All u substitution is, this method here that I'm circling with the eraser, is a way to navigate the chaos. It's nothing new. I'm not teaching you anything new in terms of integration. It's just a way of trucking through the problem and breaking it up into pieces so that it's maybe a little bit more easy to digest, because it's a lot easier to just integrate sine of u when you're not as overwhelmed by this 2 theta over 3 inside the parentheses. And so if you're not someone who can look at this off the bat and think, oh, I should have a 3/2 out front, oh, and a negative to account for the fact that this is positive sign, not negative sign. If you don't see this and then right away the wheels start turning, then I would definitely recommend that you use this u substitution. So next one, like I said, with the earlier problems, first step when you do these is to identify what is the remnants of, or what could be the remnants of the original function and what is probably the derivative. And this is one that you won't be able to figure out per se. You'll either have it memorized that the derivative of secant is secant tangent, or you won't. So in this case, u is equal to 3t. When we take du, we get 3 dt, and then dt is equal to 1/3 du. So when we plug all that in, you guys get the drill at this point. What I was saying earlier is that if you don't have it memorized, if you can't recognize off the bat that the antiderivative of secant something tangent something is secant of u, then there's no way that you're going to plug and chug and figure this out any other way. Our trig derivatives are things that we have memorized. There are proofs that exist, and if you were all that interested, you could go and read the proof and see why it works the way that it does. But as far as this class goes, you pretty much just memorize the derivatives and antiderivatives for trig things. So there's no way to come up with the answer if you don't already know that secant tangent has an antiderivative of secant. That being said, you still have to go about the use substitution process. We've got this 1/3 to factor in. And then we've got our plus c, and we simplify and we plug in. Are there any questions at this point? Okay. Another trig problem. So hopefully when you see this, you think that u is probably going to be equal to 1 plus 5t, which it is. And then we find our du, which is equal to 5 dt. And then what is dt? dt is 1/5 du. And so when we plug all of that in, we get 1/5 cosine of u du. What gives us a derivative of cosine? Sine. The derivative of sine is cosine, and so our antiderivative is 1/5 sine of u plus c, which is covered up here. And then we plug in for our original function. And if we're not confident, we can fact check. If we were to take the derivative of the inside, the 5 would multiply and cancel with that 1/5, which matches up with our coefficient of 1 here. And then the derivative of sine is cosine, so we're all good. So that's the end of our unbounded examples. Moving into a few bounded integral examples. So this one here is essentially the same as this one, only perhaps a little bit more of a complicated constituent here in the parentheses. And then we've got our bounds. So you go about use substitution in the exact same way. The only difference from when you have a bounded integral is that there is no plus c. We're going to do that deal with the line where we say from 0 to 1, or say you could do brackets too if you prefer. And then we'll evaluate. That's the only difference. The difference comes at the end. So there's no plus c, and then we're going to do our plugging in. So what's our u? U is pi t over 2. So du is going to be pi over 2 dt, excuse me. And then dt is equal to 2 over pi du. Substituting in, we get 2 over pi cosine of u du. So what gives us a derivative of cosine? That is sine. And then at this point, we're going to be doing our plugging in, or negative cosine. Excuse me. Why do I have negative cosine? I made this mistake during first recitation as well and forgot to change this. So this should be sine. I'll make these editations before I release the note later this evening. This should also be sine. And now, if you don't remember, when you're plugging in, we always do the top first, subtract it, and then we subtract the bottom. So by top and bottom, I mean we will plug in 1 into this phrase here, and then subtract the same phrase, but with 0 plugged in. And so this is what it looks like. Please, please, please use your parentheses. I'm just going to make a note to fix that, but that should be sine, and that should be sine. And it doesn't change my answer. My answer is still correct. Here, I've got the unit circle here. Sine of 0 would be 0, and sine of pi over 2 would be 1. So my answer isn't changed. Or maybe it might actually be negative 2 over pi. But generally, it's the same sort of layout, and I'll make those corrections before I send this out to you guys. But use substitution, plug in, final answer. It's no different than the other ones that we've just done, except we have that extra plugging in step because we are given the specificity of the bounds, and we're able to say specifically over this range, this is what the area underneath is. When we've got an unbounded integral, we're coming up with a generic form or a general formula that will work for the original function. But so this is asking us to do something different. This is asking us, okay, what's the antiderivative? And this is asking, what's the area underneath the derivative? What is the change in the antiderivative over this interval?
I have a question about that one.
Sure.
Why didn't you have to like do the thing where you like find where x goes from 0 to 1, but then you like plug it in to find like the boundaries for u?
Are you thinking maybe about the graphing problems? I'm not sure.
I just know because like sometimes they're like different, right? The boundaries for x and the boundaries for u, or no?
And for, I think we don't have any examples like that today.
Okay.
I know vaguely what I think I know vaguely what you're talking about, but I haven't looked at that in a while, so I don't know how to answer that question now.
Okay.
But that being said, Dr. Zlecki did tell me what problems to go over today, and so I'm not going to say you won't be responsible for it, but he didn't see it as something worth having me go over. So, and
Okay.
and he didn't have it on, if I recall correctly, we didn't go over it last semester either. But I don't want to say that conclusively. But I'm sorry I don't have an answer for you.
Okay, thank you.
Yep. Was there another question? All right. So moving into our last integration problem, well, I guess we'll be doing integration to find the areas of shaded regions, but last bald-faced symbolic problems. So hopefully you guys can identify that this 1 plus 7x is going to be our u. And then we take our du. And what is dx? It's equal to 1/7 du. And so when we plug all that in, we get on the interval 0 to 1, what is the area underneath 1/7 of u cubed du? When we integrate that, we find that the antiderivative, we've got to do our reverse power rule. So this was to the 1/3. We had to add 3/3 to reverse the power rule. So we are now at 4/3. And then we add in the reciprocal of that fraction, or we multiply by the reciprocal of that fraction in order to cancel out with that. And we maintain that 1/7, still over the interval 0 to 1. And now we're going to simplify and plug in our u. And the last step here, so the rest of this that's hidden under the gray is all algebra simplification. I won't spend too much time on it, but I will show you. If you're trying to keep up and write all of this down, don't stress too much about it. I'll send these to you later tonight after I get out of work. But suffice to say that this is the important stuff. If you've gotten up to here written, maybe to here, if you're struggling with remembering which one to plug in first and which one to subtract, this is the good stuff. This is what you need. So don't stress too much about not getting this down. So moving into some area problems, this is now section 5.1. It's still integration heavy. So that's still the concept we're working with here. Because as I've said a couple of different times, when we're finding a bounded integral, when we've got an integral that has a lower and upper bound, they're asking us what is the area underneath this derivative? What is the change in the antiderivative? So the right half of the fundamental theorem, because the fundamental theorem relates those two things, that the area underneath the derivative is equal to the change in the original function over that interval. We're not really talking too much about the change in the original function in the antiderivative. We're focusing more on the area underneath in order to find these areas. And so, so we've got some examples here that'll ask us, it gives us a few equations and it says graph it first and then find it. But we're going to start with a couple examples where the graph is given. And the graph is important because, well, let's take a look here. So we've got this interval so our bounds in this case are going to be 1, 2, 4. X is equal to 1, and then up to x is equal to 4. So we're taking this antiderivative with respect to x, so it's going to be dx. This example below is going to be dy. But what is important to note here is that we're going to find the area underneath the red function, and we're going to find the area underneath the blue function, but which one needs to be subtracted from which one in order to give us this blue region? So the function that's on top in this case, the red function, y is equal to square root of x, that is going to come first, and then we will subtract the area underneath 1 over x squared because we don't need any of this business. All we want is what's between the red and the blue, and so we're going to be subtracting this blue function. And so it looks like this. Just to throw in some, I forget this, I think they're integral operations, they might be called. So I have them starting as two separate phrases or two separate integral phrases. I'm really not sure what to call them, but you can easily combine those. That dx does not need to be there. You can easily combine those and it's still it's an equivalent statement. And I've done a fractional power manipulation so that I can do the reverse power rule. And at this point, I'm going to do the reverse power rule. I know that the original function must have had x to the 3/2 addressing this aspect of the derivative. And so I multiply by the reciprocal of that fraction in order to cancel it out. minus parentheses, -1. Parentheses become pretty important when we're doing integration, because I know that when I'm, well, this is not the reason that parentheses are important, but the reason why I have the -1 here is because since it was to the -2nd, I knew I had to add 1, reverse power rule. You guys get the drill. So now we are going to plug in. Parentheses are, again, very important. That negative gets distributed. Like with the last problem, I'm not going to spend too much time, so don't stress about writing down all of these fractions here. Final answer is 47 twelfths. And I'll send these out to you later, but it's simple integration. If you're comfortable with integration, this is exactly the same as the bounded integral examples that we've just done above. The only difference here is that there's a little bit of conceptual work to do at the front end of this problem, and you've just got to identify which function is going to be subtracted from which in order to get the correct region. And so again, the important concept here, or the what we're using to do this is the fundamental theorem, but the part of the fundamental theorem that says the area underneath the derivative is equal to the integral, or that the integral asks you to take the area underneath whatever this derivative is. Any questions on number 1 before we do another example? Okay. So now we've got an example. So with this one, a little bit easier to visualize because we got a function on top and a function on bottom. And so we can think out what function needs to be subtracted a little bit easier. In this case, we've got a function on the left and a function on the right. So let's think about what our bounds will be. We've got y equal to 1 here. So y equals 1 is probably going to be one of our bounds. It is going to be one of our bounds. And we also have 0 as one of our bounds. And so if we know that we're going from 0 to 1, we can sort of visualize that if we turned the function on its side, if we turn the graph on its side, what's going to be the top function and what's going to be the bottom function is a little bit less important in this case, but we end up getting 0 to 1 of the square root of y minus y squared minus 1, just as a way of visualizing it. And so putting those in fractional powers, doing the integration, we get 2/3 y to the 3/2 minus 1/3 y cubed plus y over 0 to 1, plugging in with parentheses. And at this point, it's just algebra. All right. So that's an example of one that's done with respect to y. We won't be doing another one, I don't believe. The rest of them are a little bit more graphing heavy, but they're not that difficult. So on an exam, you can expect a problem with respect to where you're integrating with respect to x, a problem where you're integrating with respect to y, and you're given the graph. You can expect the same and not be given the graph. So you could be asked to graph something and then take its derivative with respect to y, even though the problem probably won't explicitly say, take this derivative with respect to y. You're going to have to recognize that on your own. But what I'm getting at is we might give you the graph, we might not give you the graph. It might be with respect to x, it might be with respect to y. All right, so graphing this one, not too tough. So we've got x plus 1 is going to be a linear function with a y-intercept of 1. And then we've got 9 minus x squared. So it's going to be a parabola that opens downward and has a y-intercept of 9. And so what does that look like? We've got our parabola, we've got our linear function, and then we've got our left bound and our right bound given in the form of x equations, which we know aren't actually functions. So setting this up, we do 9 minus x squared minus x plus 1. Parentheses in this case are important. And then -1 over the interval -1 to 2 and with respect to x. So now we're going to do some simplifying before we get into integrating. So we've got -x squared minus x plus 8. And then when we integrate that, hopefully we're comfortable with the reverse power rule. It becomes x cubed. So in order to account for that 3 when we drop it when we do the power rule, got to throw in a 1/3. Same concept here. I hope we all know how to, I hope we all have a grasp on what the antiderivative of 8 would be. And again, over the interval -1 to 2. And so now we do our plugging in, heavy with the parentheses. So this is 2 examples of why parentheses are important. So we've got a negative here that's being distributed over all of these terms within these big parentheses. And then we're also substituting in values. So when we do bounded integral evaluations, we are always going to be plugging in values in it, especially when we've got things that are being cubed or multiplied, whatever. It's always important to use your parentheses when you're plugging things in. And from here, it's just algebra. And we get a final answer of 39 halves. All right. So as far as graphing this one goes, so when I first did this problem on my own before I went and checked my answer in the book, I wanted to FOIL this out. That was my first instinct, was to FOIL this out. And I thought for whatever reason, it might make it easier to graph. That is not the case. If you remember back to, it might be pre-algebra, I don't know exactly what course you might have learned this in, but graphing these parabolas, if you've got something inside the parentheses with the x, that's just a translation. And when the translation is being applied to the x value, it's going to be the opposite of what you expect. And by that, I mean, we're not going to translate the function 2 to the left because it's negative. It's actually going to be to the right. And so that's what this looks like. Just a parabola, positive facing or opening upward, and then moved 2 to the right because of this translation that we've got here. And then linear function going through the origin. So this is our shaded region. And in this case, what's a little bit different, so some problems, the bounds are obvious. So like in this case, we're given x equal to -1 and x is equal to 2. So it was pretty easy to figure out what our lower and upper bounds were going to be. In some cases, there's an additional step that you have to do. And for the next couple of problems, we are going to do that step. And that is, you have to find the intercepts of these 2 functions. So how do we do that? And by that, I mean, because the bound, whatever this x value is here, whatever this x value is here, that's going to be our left bound and our right bound. And so how do we find those? We set the 2 functions equal to each other. So we get x equal to x minus 2 squared. I FOIL the right-hand side out, combine like terms, and then factor. And we get that x is equal to 1 and x is equal to 4. So those are our bounds. So now setting up our integral on the interval 1 to 4, we get x minus 2 squared dx. And so again, I simplify before taking this antiderivative. I've got to combine like terms before I take this antiderivative. I don't necessarily have to. I can take the antiderivative of all of these terms, but you're still going to end up combining like terms afterwards, and you're just adding extra steps in having to take the antiderivative of all of these little terms. And so this is what this is the final form that I'm going to integrate. It ends up looking like -x cubed over 3, 5x squared over 2, and then minus 4x on the interval 1 to 4. So now we plug in, we use our parentheses, we plug and chug the algebra, and we get 9 halves as our final answer. All right. Any questions before I move on to the last problem? Going through the material a lot more quickly than I did this morning. All right, so we've got y equal to 12 minus x squared. So like we talked about with this example up here, it's going to be pretty similar, except our intercept is going to be 12 in this case, 12 minus x squared. And then x squared minus 6 is going to be pretty similar to this, but our intercept is going to be at 0, -6. And so what does that graph look like? Looks like this. And so since there are no obvious, we're not told x is equal to -4 and x is equal to 2, whatever it is. Since we're not given obvious bounds, we're gonna have to find what these are by setting the 2 equations equal to each other. So we got 12 minus x squared is equal to x squared minus 6. We combine like terms and simplify. And we get that x is equal to positive and -3. So that square root, you got to remember that it's possible to get -3 or +3 from these square root functions. That always tends to nip people in the bud. We always forget about that. But within the context of this problem, if you know that you need two intercepts, if you were to just say x is equal to 3, you probably think to yourself, well, that doesn't make sense. I need to know what this intercept is as well. So now that we have our intercepts, we can plug them into or we can set up our integral, do our top function minus our bottom function. Expand and simplify. And now this is our final form that we're going to take the antiderivative of. We're going to get 18x minus 2/3 x cubed. We're going to throw in that 1/3 there to account for the 3 when we drop it using the power rule on the interval -3 to 3. And then plug and chug algebra from there. So another thing that you could do to maybe save some work is you could have done 2 times 0 to 3 of the same integral equation. The only difference here is that we're going to double the area, but we're going to take it over a shorter range. So in this case, we wouldn't have to plug in this 3. We would just get 0 for this right-hand term. And then whatever this is, we would double. So that's actually, I believe, how the book did it. But I just went about it the normal way. But that would get you full credit as well on an